Welcome everyone. This is the sixth video in this series where I test different Peltier coolers and I assess and compare their performance and properties. So in this part of the series I will test the TEC12715 model, which is the 15 amperes model. So you can run quite a high current through it, so it has a very high or relatively high cooling performance. I don't have the numbers in front of me, but roughly 130-140 watts of cooling performance. And first I just want to explain what you can see here on my desk, but I strongly suggest you to check my introduction video to understand why I do all of this. Things, and also check the other videos so you can get some idea about the whole set of experiments. So as you can see, we have a watch here, so that's just for me to keep track of the elapsed time. And then there are two multimeters. This one measures the voltage and this one measures the current, because there is a slight difference between the current and voltage measured by these things and the current and voltage show on the power supply. The power supply is 0 to 30 volt and 0 to 20 ampere power supply. And this multimeter, both of them, but I'm using this, this multimeter is able to go up to 10 amperes, and since this is a 15 ampere unit, when I should measure the current at 10 amperes, I will remove this from the circuit and I will rely on the current shown on the power supply. So that's what we have about the voltage and current measurement. And there are three thermometers here. Two are in this box, temp 1 and temp 2. Temp 1 is the green wire which goes to the back side of the heatsink here. So it is measuring the temperature there. I can show it to you. This is another heatsink, but basically the construction of it or the structure of it is similar. So the hot side is attached to the top part of the heatsink, and then a thermocouple is inserted into a heatsink which is placed to the back side of this part. So that's what we have there. And then the other white wire here goes in between the fins of the heatsink, so it is measuring the temperature of the air which is coming out. So that air is basically cooling down the heatsink, and then it's going out in this direction. So that should be warm when there is a large current running through the Peltier. And then this is basically the most important thermometer. This is attached to the top of the Peltier, as you can see. I used a small piece of foam to make a good clamping force, or create a good clamping force. And then you can see that the Peltier cooler is covered by a plexiglass and some foam, so it's more or less isolated from the environment. So there is a very small amount of heat transfer, and most of the heat transfer that is going towards the cold side is not from the environment but from the hot side of the Peltier cooler. But we try to remove as much as possible heat by using this heatsink. So that's all regarding the experimental setup. Maybe I can talk about the fans. So there is one fan blowing the air in that direction, so it blows the air into the heatsink, and then there is another fan here, and then that is also blowing in that direction. So that's all basically. So there should be a lot of air passing through this cooling system, and there should be a good airflow. So what I usually do, I first measure the cold side temperature at 50% of the maximum current of this or these coolers. So in this case that is 15 divided by 2, so 7.5 amperes. So our first measurement will be done at 7.5 amperes. So what I will do, I will just turn on the power supply, set the current to 7.5 amperes, wait for 5, 8, 10 minutes and check what is the achieved temperature on the cold side of this Peltier cooler. And after that, I will measure the cold side temperature at larger and lower currents, and I will be able to see where is the minimum temperature, what I can basically achieve with this kind of setup, and what is the maximum current. And after that, I will use this heatsink, which I showed you previously, and I will put it on the cold side of this Peltier cooler. So this will act as a thermal load, and I will see how the temperature develops on the cold side and what will be the outlet temperature of the other CPU cooler, which is attached to this side of the thermoelectric device. So now, as you can see, 24.4, 24.7 degrees Celsius. So everything is at the same temperature right now. So what I have to do is I just have to turn on the power supply, check all the connections, and then start the experiment. So let's start the experiment. So first I start the cooling, and then I turn on the power supply. And then we go to 7.5. And if you remember from the previous videos, you know what is happening here, but I can explain. So this is a semiconductor, and if you cool down the semiconductor, its resistance will increase. So therefore there will be a drop in the current as the temperature changes. So I have to overshoot the current in the beginning, and as the device approaches the temperature that is its equilibrium temperature, then this drop will be slower and slower, and we can set up the current properly. So now I just slightly overshoot it, and I leave everything here for, let's say, 5 to 10 minutes, and we will see what happens to this device. So let's see what happens later. So this is the first measurement where we went to 7.55 or 54 amperes. And you can see that the cold side temperature is minus 15.9 degrees Celsius. I readjusted the thermocouple a little bit, and I added a very small drop of water to fix it to the cold side of the thermoelectric cooler and provide a better contact, because I was not sure that the foam is really pushing the end of the cooler or against the cold side of the thermoelectric device. So that's what we have now here, and you can see that we are around 30.9, 30.5 with the temperatures here. If I put my fingers on the heatsink, it's like slightly warm, but it's okay. So now this is not a lucky number because it's not an integer, so I don't want to do a half ampere step because we still have a lot of space above this current, because we are just halfway. So what I will do now is I increase the current to 9 amperes, so we will see what happens there. So let me increase it a little bit. So we reached the next let's say equilibrium. You can see the temperature is roughly minus 17.6, and this is at 9 amperes. The temperature of the hot side or the outlet also increased, so we are at 32 degrees, almost 33 degrees, and basically this is all. So my next step would be to increase the current to 10 amperes, but before that I just change the wiring here because I have to remove this. So what I do now is I change the wiring a little bit, and then I continue the experiments. So now we are at 10 amperes, and you can see that the temperature hasn't really changed. It's minus 17.7, which was basically the previous temperature as well, but the hot side temperature further increased, and I can feel the warm air coming out. So those are 34.2 and 34.4. So this is what we get from this. So now I further increase the current to 11 amperes and we see what happens. I have to check the wires because they tend to become hot. I actually had some meltdown. If you see this connection melted, or not the connection but the plastic cover around the banana plug just got destroyed, and it burned my multimeter a little bit as well, but it's not a big deal. So I increase the current and then we will check the temperature again in 10 minutes roughly. So after waiting a little bit, we can check the numbers and we can see that this temperature basically got stuck at this value, so around minus 17.4, minus 17.5, but the hot side temperature became larger by roughly 2 degrees now. So it seems like that now we are pushing a lot of current through this device, and this CPU cooler has a hard time to keep up with the heat that we generate. So I guess this will be the bottom of the curve sooner or later. So now I go up to 12 amperes and see what happens there. So this is the next step, and the temperature increased slightly. We are at minus 16.5 degrees Celsius on the cold side. So now it is really difficult for the CPU cooler to remove all the heat generated by the Peltier cooler, and that's what actually we should expect. And I have to point out that one of the viewer, Paul, noticed this from the previous experiments, so he told me this already in the comments, so thank you for that. And yeah, now it's really demonstrated that we have some problems with keeping the cold side, or sorry, the hot side cool enough. And you can see it here. We started at, let's say, 25 degrees and now we are at almost 38 degrees Celsius on the hot side, so the outlet temperature is quite warm. It's like a slight fever or something like that. I can feel it. So yeah, now things are getting warm, and as I entered this part of the room I also felt that the surrounding air is slightly warmer, and then also the wires are also a bit warmer. So now I jump to 13 amperes and see what happens. So these are the numbers for the 13 amperes. So 14.2 volts and minus 14.8 degrees Celsius on the cold side. The hot side now is getting pretty warm, so all these temperatures are above 40 degrees, so it's really high. But if you notice that this is 40, this is 14.8 absolute value, then this is, let's say, 55, so the delta T is now 55, and that's still quite close to the nominal value of this Peltier cooler. So we are like 10 degrees off. So that would mean that if we could keep this colder by 10 degrees, we might have reached 25 degrees Celsius here on the cold side, of course minus 25. So this is quite okay, and I mean, this is like a CPU cooler here, so we could improve this in many ways. So now what I do, I increase the current maybe further and see what happens. So let's go to 14 amperes. So I think we can conclude the experiment here, or this part of the experiment here. So as you can see, now we are at minus 12.8 degrees Celsius. So that's still quite cold, and we are almost at the maximum, I would say like 90%, because this is like 14 amperes, as I said. So that's really nice. But then you can see that the hot side and the outlet temperature is quite warm now, and then the voltage, as you can see, it's 15.43 watts. So enough stress on this guy with the high currents. So I rewire the current again, the current meter again, so we will be able to measure the current, because now I go down to 6 amperes and continue the measurements from there. So let's see what happens at 6 amperes. So we are at 6 amperes, as you can see, minus 10.6 degrees Celsius, and you can see now that the hot side and the outlet is much colder than previously at 14 amperes, where it was 42 degrees Celsius. So now we are 12 degrees below that, which is very nice. And then what we can tell is that minus 10 degrees is like half of the maximum cold temperature that we could produce, almost half of it. It's a bit above, let's say 60%. But nothing else is interesting here. So now we are just measuring the other temperatures just to complete the curve that I want to show you later. So what I do now is I jump down to 5 amperes and wait a little bit and then note down the numbers. So that's what we do now. We decrease the current. So I don't think that the temperature will significantly increase from this point. So I think we can note down the values that we received here or got here. So minus 7.8 degrees or minus 7.7 degrees Celsius on the cold side. So still it is well below 0 degrees Celsius. And then 5 amperes, as you can see, almost precisely. The hot side is a little bit above the room temperature. So that is 28.9 degrees on the back side and 28.3 degrees, let's say, on the outlet. And basically that. So we can note down the voltage as well. So 5.65 volts. And basically that's all what we have. So now I do a bigger jump and I go down to 3 amperes and see how the temperature changes on the cold side. So let's see what happens. So we can check the temperatures again and all the other numbers. So 1.3 degrees or 1.4, it's positive now, so close to 0 degrees, but from the positive side. 3 amperes on the current meter and 3.36 volts on the voltmeter. And here we can see that the cold side, the other side of the heat sink is 27.2 and the outlet temperature is 26.5 degrees Celsius. So now we are reaching the positive side, and I think we have like a lot of points already, so I don't continue the experiment because I think no one will use the Peltier device at this kind of performance, so there is no point to do that, to continue the experiments. And also based on this data, I already have enough points to do my calculations and charts and other types of figures. So what I will do now is I get the minimum temperature and minimum current, and then I will use this heatsink right here, put it on the cold side, and see how the temperatures develop on the cold side under a thermal load. So let's see what happens with the thermal load. So I have evaluated the data, and it says that without load I should reach the minimum temperature at roughly 10 amperes, and the minimum temperature should be around minus 17.6 degrees Celsius. But I have to repeat that this should be without load. But we are curious that about the thing that what happens when we apply load with those conditions. So now you can see that everything is assembled here. The fans are already running, and almost the same temperature can be observed on the cold side. But now I am measuring here the cold side with the heat load on, and these are the hot side temperatures. and the power supply is off. So I just turn on the voltmeter, and then I will turn on the power supply and go up to 10 amperes and wait a little bit and see how the temperatures change. So as you can see, now there is a significant change in the temperature of the cold side with the load on. So I let this run a little bit, a few minutes, and we can see what happens to the numbers, and we can see what's the temperature on inside the heatsink. So I will poke in the thermocouple and see the other stuff, the other temperatures. So yeah, let's wait a little bit and see what happens. So I think the system was running for quite a time now. It has been running for like 8-10 minutes. I haven't really checked, but more than 5 minutes. So we can say that this is more or less the equilibrium. So you can see that the Peltier device on the cold side with the heat load on it is 8.8 degrees, and then the hot side and the hot side's outlet is around 36-37 degrees Celsius. And as I said, we are at 10 amperes roughly. So this is what we got here. And I can feel again that quite cold air is coming out. So let's see the temp too. So now I remove the outlet temperature thermometer, and I put it in the middle of the cold side in the same fashion. So I just squeeze it in between two fins, and let's see what happens. So if you remember, the room temperature was around 25-26 degrees if we measure it with these thermocouples. And you can see that the temperature now is going down slowly. It's like 0.2 degrees per second, something like that. And it's around 22 degrees. If you remember, or if you check the previous video, you can see that the number was 22 degrees there as well. But here it might be so that, yeah, it goes down below 22 degrees, which we should expect actually, because this Peltier cooler has 50% higher cooling performance than the 10 ampere unit. So that's quite a large difference, and it should be noticeable. But it takes some time, and you know, a lot of air is mixed here together, so maybe we are picking up some warm air which goes through this cold side CPU cooler, which means that we are already pushing through some warm air through this heatsink. But it's 22 degrees, and I can feel also that this provides a nice breeze. If I just push this thermocouple against the back side of the cold side CPU cooler, then that's what we get there. So it's like 18.3, 18.2. It's cooling down slowly, but I don't know if it worth the wait. Now I just replaced the cooler to somewhere else. We can see that with the thermal load this goes down quite nicely. And then if you remember from the previous videos, I was moving around the thermocouple on the surface of this Peltier, because I can demonstrate it to you. So this CPU cooler is covering roughly 35 by 35 millimeters, so some of the edge of the Peltier cooler is exposed. And then I try to push the end of the thermocouple next to the edge of the heatsink of the CPU cooler, where it is in contact with the Peltier cooler, but it's not always that easy to put it there. And sometimes the Peltier cooler or the thermocouple is placed somewhere else on the Peltier cooler, so maybe it's closer to the edge, and that means that it is a bit further away from the area of the heat transfer. So here the Peltier cooler can actually go down to a lower value. So now I will, instead of putting it here where we measured roughly 8 degrees, I will put it here, and we will be able to measure even lower temperatures. So let me demonstrate it to you. You can see that now I put it against the edge almost. It's let's say like 3, 4, 5 millimeters from the very edge, and we are almost at 0 degrees Celsius. So that's like quite a difference as compared to this. When now I'm touching the heatsink, the CPU cooler, the side of it. So then now we are measuring like 8.3 degrees Celsius. So that's what's happening. I can probably demonstrate it to you with this. So this is an unused CPU cooler, is the same as this one, and then so this is the area which is in contact with the Peltier, and then I put it right here. So roughly in the middle, I try to put it there and put it right next to this edge, what you can see here. So it is touching the surface of the Peltier cooler, and it is in contact also with the this part of the heatsink. So with that we can sort of get an impression of the heat transfer. So I do it again. I just have to fix this. So you see it's 12 degrees, 13 degrees, depends on where I put it. But yeah. So it is what it is. But what we could see during this set of experiments, that the minimum temperature of all these things are roughly the same. So let's say it's around minus 20 degrees, but it strongly depends on these temperatures, what I read, which is basically the room or the hot side temperature. The higher you go with the hot side, the less you get further away from 0 degrees. So of course you have the fixed delta T, let's say 60 degrees. So if you are at 60 degrees on your hot side, then you cannot go below 0 degrees in principle, because you cannot really you cannot really cheat the physics. I will show you with another set of experiment later on, which will be another video, that I will stack 2 Peltier coolers on top of each other. Probably I will put the strongest one on the bottom, so that will be in direct contact with the CPU cooler, and then I put the weakest one, so the 3 ampere, on top of it, and then a large heat transfer can be achieved, and we can see how deep we can go with the 3 ampere unit if its cold side is very, very cold, let's say minus 10 degrees. And can we go down to minus 50 or minus 60 or even lower? We will see. But this is what we got now here. I can feel that this CPU cooler here is blowing very nice cold air at me, but still I have to emphasize that this will not be good for AC. So this cannot be built into an air conditioner in this setup. Don't even try it, because you just waste your resources, but it's a very fun experimental tool. So what I want to tell you is that now I finished with the 5 measurements. So 3, 6, 8, 10 and 15 ampere Peltier coolers were tested in this series. So I will stop recording this video, and in the next video I will evaluate all the data, and I will try to discuss something about these Peltier coolers, and show you some hopefully nice charts and graphs, and show you some useful data, and basically that's all. So I hope that this video was useful for you or entertaining, and you learned something, and see you in the next video.